And, you know, everything, and I mean everything that we cover this semester, large majority of it goes to his credit, okay? You know about calculus. He developed calculus, him, and was it Leipzig? Helped him a little bit there. Leibniz, yeah. I never can remember the name. I can get screwed up. But anyway, sorry, dude, wherever you are. Everybody messed my name up, too. They always said Gerard. So, you know, anyway, so I know how he feels. I feel his pain. So, everything we cover, of course, is Newtonian, all right, this semester. Now, it's pretty interesting, too, how he made his, or how he derived his equations of motion, okay? We'll look at that here in a second. So we're looking at forces. And again, y'all, this is elementary stuff. I mean, you know, you've known since elementary school, teachers say, push it, pull it, okay? Well, what are you doing? You're putting a force on it. You're causing, you know, push and pull. You're causing motion, okay? And again, a force, how do we define a force? We'll do that in just a second. But again, simply put, it's a push or pull, okay? And of course, we write it as F. And notice it has the little vector arrow on top. Yes, it is a vector quantity. Please remember that. We're not going to hit scalar until we hit work, okay? Work, direction does not matter, all right? And we'll explain that when we get to that, okay? You say, well, wait a minute. What if you apply an angle? Well, we'll get to that, okay? All right. So there's basically 4 types of forces, and listen, you better get this, okay? There are 4 types of forces. Normal forces. Anytime you have a normal force, the force is what? Okay? Again, y'all, this is conceptual stuff now. Terminology, conceptual stuff. It is always going to be perpendicular to the surface that it rests on. Well, what if the surface is angled? It is still perpendicular with that surface. Does that change, though? Does that change the amount of force if it's at an angle? Okay? All right? Because when we look at it, and when we start looking at frictional forces, you're going to see that our equations are going to become a little bit more involved. All right? On a flat surface, it's easy. On an angled surface, we have to use sine and cosine. And here's where, now boy, I'm telling you, I've been harping about drawing, label. I'm going to tell you right now, it's fixing to get real serious about that. You have to draw, you have to label, okay? Because the equations are not going to make any sense if you don't, okay? All right? They're not going to make any sense if you just try to memorize a bunch of stuff, okay? You got to draw it, okay? You got to draw it, okay? So that's one force. Frictional force. Well, everybody knows what friction is. Anything that opposes motion, okay? Frictional force opposes opposition. Is op 1 or 2 P's? I can't spell with opposition. Yeah, I thought it was. I can't spell with flip anymore. Opposition, okay? Oppositional forces, all right? Frictional force. Notice how we write it too. Lowercase f, a little script f, okay? So force is F. Frictional force is that right there, okay? Now, what about normal forces? Now, normal forces, your book will write it this way, but I like to write it this way. This is F of N. I call that a normal force. Okay, that's the way I like to write it. Okay, that's the way I like to write it. Okay? All right. But you don't have to, but that's the way I write it. Tensional forces, notice it changes to a capital T. Tensional forces. All right? This is not a tensional force. Well, it's actually, well, no, it's not compressional either. That's just a plain old force, okay? I pushed it, push-pull. All right? Tensional forces, if I pick the table up, okay, tensional force in my arm, in my joints, okay, street light, not street light, red light, hanging from a cable. Now you civil engineers and you electrical engineers, especially if you work for, who'd you tell me you work for? County, yeah. Civil engineers, electrical engineers, if you work for, say, Alabama Power, Marsh DeKalb, you know, I don't know if you ever wondered, but how do they know how many poles to put up and how far apart to put the poles? Now, Alabama Power, I think it's 200, 250 feet they put a pole. Marsh DeKalb does it, I think, every 100 and 175 feet. And that's why, and I'm not dissing nobody, but typically you don't have as much power outages with ice and snow when the poles are closer together.
Also, stuff depends on the diameter of the wire.
That too, yes. Mm-hmm.
Larger the wire,
Yeah.
a quarter inch of ice between
Yeah.
200-foot poles.
Yeah.
It'll pull a line.
Oh, it sure will. And so here we get into the tensional forces of how far to put our poles apart. Even the brackets that the insulators and things they use, those are tensional forces they have to calculate for. All right? Okay. I was going to a Bama game a year or two ago, and I was going the back way, and I noticed some of the lines were, they had to mount the poles, and they kind of had to mount it on the side of a hill, and they tried to get it as straight as they could, but I could tell there was a lot of tensional force, so they had several cables opposite. You know, the line was on this side, and the cables, the stabilizer cables, are on the opposite side. Well, I mean, that's commonsensical. But again, you do a lot of those calculations, these types of calculations, when you're hanging cables, hanging street lights, I said street lights again, red lights. You may have some street lights hung on cables. I've seen them like that, okay? So we got what? We got normal force, we got frictional force. What else we got? We got tensional force. And then here's one, plain old weight. Now we typically do write weight, just W. You can write it this way, F of W. You can write it that way, okay? And so we'll get to the units in a minute, okay? And notice they call this a long-range force. Now I won't get to the equations yet. We'll get to that in just a second, okay? All right? So notice the weight is what? The force of gravity, right? And it's always what? Straight down, always. That's right. That's exactly right. Okay? If it's like this, it's still straight down. Okay? And here's where your sine and cosine is going to come into play. Okay? Yeah, on Earth, yeah. Unless we're going to Mars. Okay? All right, so now you don't have to write this down. This is just some common magnitudes. Notice right here, y'all, the gravitational attraction between a proton and electron, and then the gravitational traction between a proton, electron, and a hydrogen atom. So notice the amount of forces we're dealing with here. Okay? Now, when we get into electricity next semester, hopefully all of you will be with me next semester, and if you don't need it, I can understand that. But anyway, you're going to see there's a huge difference in gravitational force and electrostatic force. Okay? Yes. Yes. Yes, it really is, yeah. Okay? And I'm going to tell you, if gravitational force was like electrical force, reckon what would happen?
We'd all be stuck in the singularities.
Yeah, sure would. Yeah, we'd have our heads shoved down in our feet. Basically, if you want to think about it in terms like that, or a point of singularity. That's a good description too. Okay, all right, so again, now this talks about drawing force vectors. Y'all, again, I'm telling you, this is so important. You've got to draw the problem. You've got to draw the direction of the force. If it's at an angle, you need to always draw it, show your angle, the amount of force on the vector. Okay, you got to, y'all. I'm just telling you, it's so important, okay? All right, now, one thing about forces, the superposition principle applies. And what do we mean by this? In other words, if you have a force pulling in two directions, you're going to have, here's this word again, components. You've got X and Y components here, and you've got X and Y components here. Now let me ask you something right here. What are the Y components on this force vector right here? Zero. Because we know the sine of zero is what? Zero. However, this vector has both X and Y. This one only has X, or I, okay? I and J. So please remember, when we talk about superposition of forces, basically what we're talking about is when forces are at an angle, then you have to you have to determine the components, and you have to add them together. And then if you want to find the magnitude, if you want to find that right there, you got to do what? Square the squares, okay? So really and truly, y'all, we're kind of getting repetitive here. Our equations will change a little bit.
Could you say that it's the angle between the other angles?
Yeah, yes.
Between the vectors?
Yes, you could. You could. Yeah. Okay? All right, and again, it's important. Now notice here it's on an incline. Now we're not going to hit inclines to start out with, but we will chapter 5. Okay? All right, so notice on an incline, well, here's where we get into our sign, and here's where we have to draw it and label it and say, okay, we're looking at this force, we're looking at this force, or we're looking at the force in this direction. Okay? All right? And sine and cosine definitely come into play. And you'll see when we get into chapter 5. I don't want to throw too much at you right to start with. Okay? So putting on an incline changes everything. So notation for vector sum, very important. Now, you can write it R, but typically this is what I will say, that the sum of all forces are equal to F1 plus F2 plus F3 ... Okay? And what do I mean by the sum of all forces? All forces involved. Notice we have force 1, we have force 2. Okay? What are we going to look for? We're going to look for that right there. So we say the sum of all forces. Bam. Yes, we've got x and y right here. You're going to have to find the components. And x and y right here. You're going to have to find the components using sine and cosine. All right? Remember how we found velocity in the x? It was initial velocity cosine theta? Well, guess what? If I want to find the force in the x, guess what it's going to be? It's going to be the force of that vector, let's just say 1, cosine theta, and f in the y for vector 1 is going to be what? F1 sine theta, right? Yes? And then you do the same thing for vector 2, force 2, correct? Is that making sense? Okay? So I'd use sine and cosine here to find my I and my j, or x and y, and sine and cosine on this one, and then I'm going to do what? Add like terms and square root of the squares, right? Add my x's, add my y's. Okay? Now, angles. How do we do angles? Now, again, some of you did it like I told you to do it and said counterclockwise positive x-axis, and some of you didn't, and I might have counted off a point. Okay? Always remember, angle. Okay? The angle. Okay? Now, another thing, what do we remember about vectors? Can I move them around? Sure. As long as we do what two things? Keep the magnitude and the direction the same. So if I wanted to, I could actually come down here and I could put this vector right here, or I could move this one up here, couldn't I? But you want to remember, y'all, counterclockwise from the positive x-axis. Okay? When you determine the angles. Why? Because then I don't have to worry about, oh, I'm in the second quadrant. Oh, well, this one's in the third. Whoop, this one's in the second. This one's in the first. Oh, yeah, if it's in the third, I got to make both of them negative. It's in the fourth, y is negative, x is... You don't have to do that. You just do it counterclockwise, put the angle in, and guess what? The sine and the cosine will make it negative, won't it? What's the sine of 270? Negative 1. Right? What's the cosine of 180? Negative 1. See, I don't have to put it in. The trig does it for me. I'm telling you, it saves you a lot of heartache. It saves you a lot of heartache. Now, you will see, and I'm trying to remember if this text, I think they try to stay away from doing this in this text, but now I've seen textbooks, it gets confusing because they'll do it and then they'll do it both ways. And I hate that. Pick a way and stick with it. All right? Don't get so dang wordy. And I agree. Some of these problems in these chapters, they're good. The people are good. They know what they're doing, but they're too dang wordy. Okay? You know? And it don't need to be. All right? But, you know, sometimes I'll see them and they'll work it and they won't do it counterclockwise. And they'll put in a negative and like, whoa, what is that? Okay, so counterclockwise, positive x-axis, you always will have the correct sign, okay? And you'll see what I'm talking about when we get into some problems. Okay, here we go. All right, so please remember that. Please remember, I'm going to tell you, everything we're covering is very important, okay? All right, so, all right, what do we mean when a body is in equilibrium? Okay? Well, notice right here, if it's in equilibrium, here's some terms you got to remember. If it's at equilibrium, if it's at constant speed, what is acceleration when we have constant speed? Huh? Yeah, these are terms you need to remember. Oh, it said it's at equilibrium. So that means what? What the heck does that mean? All right, the sum of all the forces acting on a body at equilibrium is equal to 0. Now, here's what messes with us. So you mean tell me there's 0 forces on the object? No. There's no net force. Okay? In other words, am I making sense? I hope so. In other words, no net force. Why? Because it's not accelerating. Okay? It's not accelerating. All right? Now, I know some of you are thinking, what about G? G is always present. You're exactly right. Okay? But you can have G involved, and you will, and still have no net force. Okay? All right. So you'll see when we get into it. All right? So Newton's first law, which is also known as what law? The law of what? Inertia? Is that right? Because why? What does this mean? What the heck does this mean? All right. Is that object moving? No. Is it obeying Newton's first law? Yes. That's simple. Yeah, now, if I do an outside force on it, it's no longer obeying Newton's first law. It's going into the what law? We haven't got to yet. Fix it to. Second law. Okay, but now it's back at Newton's first law. All right, when do we really, now this one's a little bit hard to wrap our, well, I say it is. You see it setting still, but you think, well, yeah, it's going to sit still because you're not moving it. Exactly. But if you go into space, you work on the space station, and you're out there in your little jetpack, okay? I'd love to try that. I always wanted to go up and shuttle. My wife said, heck no. You're not going up because those things blew up, didn't they? Some of them. 2 of them, well, one of them burned up, one of them blew up, yeah. Yeah, and you know what caused the Columbia to burn up? Somebody forgot their chemistry.
Yeah, so the ceramic tiles were the wrong composition in the wrong spot.
Yeah, and 2, galvanic corrosion. Dissimilar metals touching each other.
That was Columbia?
I believe it was Columbia. Challenger blew up, Columbia burned up.
Yeah, Columbia.
Yeah.
Challenger was the O-ring.
Yes.
That's all the O-rings that they knew about.
Yeah, yeah. But I'm serious. Somebody forgot basic chemistry 101. They had dissimilar metals touching. Those tiles had a metal backing. Well, the frame of the shuttle was metal, but they were dissimilar metals. I think it was iron and aluminum, and that's a no-no. That is a no-no. Same thing with iron and copper. Copper and aluminum. Basically, yeah, unless they're close to each other, on it, that, you know, like zinc and iron. Well, why will zinc and iron not galvanic? Well, because they're close enough to each other to where there's not a huge exchange of electrons. But now,
Reduction potential.
yes, reduction potential. That's right. Okay, okay. So please don't forget your chemistry too. All right. So I said all that to say this: when you're in space and you're working, okay, Newton's first law really comes into play. Well, they all do, but the first law, for example, you let your screwdriver go. Well, if you don't have a string hooked to it, because see, when you let it go, just doing that right there, you're applying a force to it. And if you don't have a string hooked to it, it's going to go, and it's just going to keep going. You've all seen videos of people on the space station, a shuttle, and they're monkeying around. They take their pen and twirl it, and it just sits there and does what? It just spins and spins. Never slows up, never speeds up. Same velocity. Newton's first law. Okay? Newton's first law. Okay? His third law is best demonstrated in a swimming pool. That's why the astronauts work in a pool, full gear. Why do they do that? Because that's the best earthbound demonstration or application of his third law. Okay? You ever wrestled with somebody in the pool and your feet wasn't touching the bottom? Really hard, isn't it? This is where the small dude could overcome the big dude, right? Somebody like me. Why? Well, because our feet's not touching the bottom. Of course, it'll be hard for him too. But still, you're floating. Okay? All right, we'll get to third law. Okay? All right, so how do we, Newton's first law says then what? That, well, shoot, that's not what I wanted. All right, okay. All right, so his first law says what? That when we apply, that's second law, excuse me, that's second law, I'm sorry. First law, the sum of the forces is equal to what? 0. If we are at what? Equilibrium. Right? So please remember that. But now what about if we apply an acceleration to it? If we give it acceleration, then we get into Newton's second law. Okay? Let me open my text. All right. Yeah, we're on page 106, 106, 107. Okay? All right, but besides this, if it's not accelerating, it's Newton's first law, law of inertia. All right, let's move on. All right? All right, now, well, dang it, it's not what I wanted. I wanted where it comes to second law. There we go. All right, so now let's look at his second law. Newton's second law says what? That when we apply, if we apply force, the object accelerates, doesn't it? In the direction of the force. Right? Best demonstrated with a chair. I apply force to it. What does it do? Momentarily, it accelerates. Okay? Why did it stop? Friction, yeah. Number one thing, friction stopped it. Friction with the floor, friction in the bearings. Okay? Friction. Friction's always the killer of forces. Okay? And that's something that, especially if you've got moving parts, you do not want friction, or you want it small. That's why we put oil in an engine. It reduces friction big time. Okay? Okay. Now, here's your units. Please write this down. And you do need to remember that it is a kilogram. All right, let's look at it. F's equal to MA. Let me erase. All right, so F is equal to MA. And so we got a kilogram times a meter per second squared, right? So we apply, by definition, this is how you define it. When you apply a 1 Newton force to a 1 kilogram object, it will accelerate at 1 meter per second squared. Now, what is the relationship to force and acceleration? Acceleration is equal to what? The force divided by the mass. So the relationship to acceleration and force is what? Directly proportional. Directly proportional, right? If the acceleration if the force increases, the acceleration does what? Increase. All right, what about mass? What kind of relationship is there with mass and acceleration? It's inverse. Now typically, an object's mass is not changing unless it's a rocket, of course, taking off. And there you get an exponential curve, don't you? The rocket's taking off, the mass of the fuel is going down, therefore the mass of the rocket's going down. So you get an exponential relationship between mass and acceleration. It increases, the acceleration increases exponentially. That's why when a rocket takes off, it's slow to start with, but it doesn't take long. By the time it gets up, 10, 15,000 feet, it's really starting to move on. Really moving fast. That's why, because it's losing mass as it's accelerating. Okay? Okay. But besides that, okay, if I push that chair, the mass of that chair is not going to change. The only way it's going to change is if I put books or something in it, or put you in it. And then what will happen if I do that? If I put you in the chair and push it with the same force, what will the value of acceleration do? Go up or go down? It'll have to go down. So please remember that mass is inversely proportional to the acceleration, directly proportional to the force. Okay? Very, very important that you remember that. Now again, typically we don't change the mass during motion, unless it's a rocket. Okay? Like a car. Car's mass is not going to change while it's moving down the road. Okay? Not going to change unless somebody T-bones it and cuts it in half. Heaven forbid. All right. Okay? All right. So there's your units. Please remember those. Now, how did he come to these equations? And I know I haven't gotten the momentum yet, but he actually took momentum and he did the derivative. Because what is if you take momentum and do what? dv over dt, what are you going to get? And put m out here as a constant. What are you going to get? You're going to get, what's the derivative velocity with respect to time? You're going to get ma. That's really how he derived his laws of motion. He took momentum and derived the velocity with respect to time. Well, derivative of velocity with respect to time is acceleration. And so that's how Newton derived his equations. Okay? Okay. That's how it was done. All right. Any questions? Now, here we see some tables. Y'all, I'm not going to ask you. I just want you to be familiar with it, okay? We're going to do everything in meters per second squared, but there is such a thing as called SIGS. That's how I pronounce it. CGS. Centimeters per second squared. So there are other ways of measuring acceleration. Notice the force is called a dyne. And notice what mass is used. Gram, not kilogram. Okay? So if we're dealing with SIGs, your mass is in gram and your acceleration's in centimeters per second squared. What about the British system? Now this is the one we're most familiar with. Feet per second squared. Feet per second. You know about the shuttle, not the shuttle, you know about the Mars probe some years back? They made a huge error. They were monitoring one of the probes coming in the atmosphere of Mars, and they were watching their data coming back at them. And they were thinking that they were reading it in feet per second, and they remembered too late, that it was actually what they were reading was meters per second. Okay? Why? Well, they built, if I'm not mistaken, everything was built to feet per second, but everything read on their screens meters per second, and they got confused, and they thought, oh, it's doing great. It's coming in at 1.5 meters per second squared acceleration. No. That's like, well, meter's 3 feet, isn't it? A little over 3 feet. So we're talking 5 feet per second. And so it impacted on the surface, and they thought, okay, we should start getting some readings here in a minute. Nothing. And they kept scratching their head, oh, something's wrong. Go back and check it, Nothing. And then it finally hit somebody, and they went, oh, my God, that was meters per second, not feet per second. I guarantee you some engineers went home on that one. They probably says, get your calculator, get your protractor, your laptop, go to the house. We no longer need you. Because that was, $50 million probe.
It's kind of like when they built the Hubble telescope.
Yeah. Yeah, they sure did. Can you believe that? And how much was that sucker? It was what, 75, 100 million, 150 million? And then they got it up there and it wasn't, the images, something was wrong. I thought, man, there's no way these images are right. And then they got to checking and the mirror was off. And so they had to go back up and fix it. And I forgot how much it cost to fix it. 40 or 50 million. Whatever a shuttle trip was, we don't use it anymore. But they fixed it, and it was a huge success because you realize those big old gloves. Can you imagine using those big old gloves and then little screws like this, trying to hold them? Can you imagine doing that? But they did it. They did it. Fixed it. So we can work in space. All right, now look. Okay, so Newton's second law, F equals ma. Real simple equation. I like simple. How about you? Yeah, me too, Teach. I think you're going to like this better. I'm not saying we're away from kinematics, though, but I think you'll like this a lot better. Weight is simple. Look, y'all, that is F is equal to ma. Come on, y'all, look. That is acceleration, and, of course, mass. We just changed the symbol to W, okay? So it's basically the same equation. It's just we're looking at from a different perspective, okay? We're looking at the gravitational pull, okay? All right, any questions on that? Now, needless to say, you know that their value for G is going to be different, and what is that dependent on? Well, it's dependent on, of course, the mass of the planet. Has a lot to do with it, okay? We hadn't gotten to Newton's law of gravitation, but we'll look at that. But that has a lot to do with it. When you look at the moon's gravity, you probably know this, is 1/6 the Earth's gravity. I hate this pen. Okay? It's 1/6 the Earth's gravity. Okay? All right. So if it's 9.8 on Earth, what is it on the moon? It's what? 9.8 times 1/6 or divided by 6. 9.8 divided by 6. What do you get? Like, yeah, 1.63. I started to say 1.6. Yeah. So on the moon, you bunny hop. It's actually easier to bunny hop than try to walk, because every time you walk, you bounce. You kind of, And so they bunny hop. They bunny hop. I went to space camp for teachers. First year I was a teacher at the end of the first year. And it was pretty neat. And learned a lot of interesting info. Now, boy, you're talking about some lectures that were way up here. But it was interesting. It was really interesting. I learned a lot. We got to simulate how they did that. And basically what it was a bungee cord hanging from the ceiling with a seat. And they made the bungee cord tension similar to what you would have to deal with on the moon, and you bunny hop. That's how they trained them for it. Okay? You ever see any videos, that's what they're doing, okay? Okay. All right, and I think I want to stop right there, okay? All right, let's look at some problems. Any questions?